So we will play around with the Hadoop file system a bit more now. And there were some slides that we put that says RAID demo. Again, the slides are mainly for me in some sense. It's got some things here that will execute and some outcomes. But I stole this from somebody's copy. So if you're missing it, you can grab it from me later. But it doesn't really have too much on there to excite you anyway. So did you have the? Oh, I don't need that. So I just need the laser pointer. Before we start, I think if you remember when we were looking at what processes were running on our Hadoop system, there was a RAID node running there. And that, if you remember when we talked about compiling Hadoop file system and installing it, that was kind of an add-on. You needed to kind of get that separately, add it on, and compile it separately for it to work. It's a separate module. And I'll just say a little bit about it. It would have been good if we had some slides perhaps on it. But that's the part that we've concentrated on. When we change the system to build our own codes, that's the part of the source code that we need to change. So that RAID node is it's some sort of component. It's running as a process, and it's essentially monitoring a directory space in the Hadoop file system for files that are there that need to be rated. Okay, there are some conditions, that the file needs to have a replication of 3 or more. These are all parameters, in fact, for the RAID node module. And then, once the conditions are triggered, once they're all met, then it will RAID the file. So ordinarily, and we'll always talk about files conveniently with 10 blocks. Okay, we'll construct files that have 10 64 megabyte blocks. So you would have 1, 2 down to 10 blocks in a file, and ordinarily, and what we will see is that you have three of them, right? So you have 1A, I'll just call them 1B, 1C, right? This is what we're used to seeing. I'll just be complete and put 10B and 10C, right? So this is what the file, how it would be stored in the system with replication. And that's good. Replication is good when you're doing processing, like the MapReduce jobs and so on. It gives you extra ability to access things. Although in our particular example, I didn't actually show it, but when we ran MapReduce, it was only using as many mapper functions as what there were blocks in the file, because each block really only had to be read by a single. There was a single task that could do it. You couldn't have several tasks reading from the one block for that particular example. But if you could, you can use other blocks as well to get parallelism in the read for the same copy of of that block. But our processors didn't do that. But anyway, so what the RAID node is doing is it's monitoring files in the directory, and then when it's triggered, it goes through a process. And the first process that it does is it eliminates, it reduces the replication. So it sets the replication back to 1. So, and we did go through that, and I think it can pick at random, 2 of these, right? But let's just say, for simplicity, we eliminate all of the replications, and then you're just left with replication 1, and then it does the coding part where it will go and construct, and I'll just draw over here, a number of other blocks, and it will depend, the parity blocks on exactly what code that you're using. But it will construct these all on the same node, and in fact, where these blocks are as well is kind of random, which data nodes that they're stored on is kind of random, right, where they are, and where these blocks are just puts them somewhere on a data node when it constructs. So there's the first step is the replication is set to 1, and then it's coding, create the parity blocks, And then there's something called a placement monitor. A placement monitor. And the placement monitor is constantly, it's getting a histogram of the blocks placed over the data nodes for each of the rated files. So it's really finding where they are. And what you don't want is too many blocks obviously sitting on the one data node, because if the data node fails, you end up then losing too many blocks all at once of the one file. So you need to spread them out obviously so that you get the reliability. So that the placement monitor is sort of regularly running and checking this histogram and moving blocks around. There's a block movement function inside Hadoop. It's called a block mover. And the block mover, you can give it a list of blocks that you want to move and where you want to move them to and stuff like this, right? So the placement monitor runs and it keeps looking, and anytime it sees a set of blocks that is not a good configuration, too many on the one node, then it will start pushing them around onto other nodes. And these were the things that we had to look at, and when we were implementing our code, and that to change in the source code of the RAID module, which we may talk about a bit later as well in the when we talk about our locality aware codes. So that's just a very quick kind of notion of what this RAID module, what the RAID module, RAID node it's called here, is doing. Let's have a look. Now, we're going to, you have to sort of bear with me a little bit. The practical thing takes, there's delays as we copy stuff or create stuff, so it can be a little bit delayish, but we're going to, and part of that delay is because we're going to try different codes, and the system doesn't like it when we just change the parameters of the code, while it's running. So what we end up doing is kind of, deleting the entire system, starting at scratch, for each of the code parameters that we put in. Otherwise you start getting errors where it gets confused. It was thinking it was using one code and suddenly, you've changed it to another code. So what we'll do is, there's a few things that we have to sort of look at. One is the configuration of the RAID node itself, and I'll just quickly have a look at that. We put that file inside. RAID. So this is the RAID configuration file. I was playing with it earlier, this morning. So I'm going to turn it off, right? To start, we're going to start from a situation where there's no RAID working. So, I can do that. If we just have a quick look in here, it's sort of, these are some of the conditions I was talking about. So pick files for RAID only if their replication factor is greater than or equal to 3. Target replication, so after raiding, what kind of replication do you want? And the meta replication, not sure actually, that the time in milliseconds after a file is modified to make it a candidate for raiding. So there's a bunch of parameters there. I'll just turn that off. So what I did with the source prefix, I said there's no source prefix, so don't do any raiding. So what we'll do is we will, I'm going to stop everything, which will stop, it really does stop everything, stops the entire system. And then we have this script called update nodes, and what that does is it logs into all of our nodes and just deletes everything from all the data. So really there's nothing that the data nodes will, when they scan the directory, there's nothing there, right? So they're not going to report any blocks that are from a previous experiment. Doesn't take too long to do that. So we do that. And now I'm going to format the name node as well, right? So this really does remove the file system image and the edit log that we talked about that the name node keeps. So this is like formatting your file system, right? It's done now. This is completely start from scratch. So now I'll start up the distributed file system. and you know, so it logs, you know, okay, so it's started up all those things, and we'll start up MapReduce because we're actually, when we construct our test file, we're going to, it's a job actually, it's a MapReduce job that constructs the file for us. So we'll start up MapReduce, the job tracker, and all of the task trackers will start up. So okay, so now we're going to I'll go into our Hadoop installation. Let's just have a look. So it's got that stuff in it. And now there's a HD Zorbus test jar, that's this one, that gives us a few things. Basically all that we're going to use it for is for constructing a 640 megabyte file that will give us exactly 10 blocks using a MapReduce job, and the file will just have zeros in it or something like that, just dummy data. So we'll run that job. Actually, I don't need to type, I can just type this. When I could have actually tested first that the file system was up and running by, you know, just doing an ls of the root directory and see, yeah, it's okay, maybe doing a file system check, seeing it's okay, but I won't test that right now. We'll just go ahead and so this gives us a program called test distributed file system IO, right? And I can tell it to write files, and I'm just going to tell it to write one file, and the file size in megabytes we'll put 640, or not gigabytes, 640 megabytes. So it'll write a 640 megabyte file. It will take a couple of minutes, I think. I think we can see I've got over here, what have I got? I've got this is the file system web page, which sort of says it's up and running. In fact, we could browse it here. And there's just a couple of directories that have been constructed. There's also the MapReduce job tracker daemon, which says that something is being run right now. So while that's running, you know, yesterday we went through and we looked at the rack placement. You remember, of the nodes, and I went in and I actually grepped the IP addresses to see which racks they were on. And we found that they were all on different racks. Instead of two nodes being, two copies being on one rack and the remaining copy being on a different rack, they were spread out over 3 racks. I didn't know why. I found out that it had been switched off. Yeah, I guess the students were running some other tests where they wanted to, to turn that particular strategy off. I switched it back on. So when we see this file, it will. When this is done, we'll be able to have a quick look at that as well. I'll just run another terminal. And we'll log in. Because we'll have a look at in the configuration file for Hdfs, there's a few things that we will need to look at later as well. There are some of the things that we talked about before. So block reporting interval, how long before each data node reports about the blocks that it has, right? So we can change that interval. It's set at 30 seconds. Every 30 seconds, the data node will report, the blocks that it has. So that kind of determines the delay in between, knowing when something has gone down. The default replication is 3. This is where we've set the RAID config file, right? So stuff like that that's needed by RAID node. And some other things. One thing that was, there's a rescan interval, it's 30 seconds. There was, and there's a few things in here. Placement policy, the class for running the placement policy, so you can kind of substitute that with your own class if you go and compile your own class, a block placement policy RAID, you can put your own class in there, and it will use your class instead of the existing one, right? So that's just part of the you know, where the file system is. And then there's a few parameters here that you know, Hdfs RAID parity length that is set at 4 and 4, and in fact for the first RS code, those are the parameters that we will set at. If we keep going, we'll see block fix interval again at 30 seconds, the interval in milliseconds between checks for lost files. So, you know, default to 1 minute, but this is set to 30 seconds. There's the heartbeat interval, so the data node heartbeat, we talked about that. That's set at 3 seconds. Right, so all of these things you can kind of go through and play with. And you know, when we use MXOR codes, the multi-XOR codes, we'll turn that on, and so on, right? So, so there's a bit there. There's something I just want to check because I didn't see it when I was scanning down, and I'm wondering, is it there or not? And yeah. So this particular property, the script file name, wasn't there before. It had been removed, and that script is what Hadoop calls to find out which rack number a particular IP address belongs to. So there's the rack topology that we showed that had the numbers there for every IP address, what was the rack number, right? And we assign numbers based on, because we know that the IP address where it is. So I know that these IP addresses are in Melbourne, so I give them all the same rack number. And I know that these other ones are in Queensland, so I give them all the same rack number. These nodes have changed a bit, and I dare say that if I investigated a bit further, that maybe some of those assignments are wrong now, and I should probably update them because the cloud system that we're using has changed. We've moved nodes around, and you know, you have to keep that up to date, otherwise the optimization won't work properly. This thing's finished now, so it wrote a 640 megabyte file, and the location of that is in a specific spot. Just let me, so let's just look, I'll do file system check, and it's in benchmarks, test DFS IO data, and it's, what's it called? I've forgotten what the file is called, so I'm going to have to do something else first. I'm going to have to do just an ls and see what's in that directory. So it's called testio0. I can see that it's 640 megabytes. Now I'll do my file system check, and we'll have a look at it. Sorry? Is there a question? No. So, is it clear what we're doing?
That's what I was saying. If they have some questions.
Yeah, ask if you have any questions. Really, you know, you could stop me any time, right? I'm not just like a script that's running. I'm interactive. You know, you can pause, rewind, fast forward, or do all those sort of things as well. Right? So we'll have a look, and there's a command that I didn't know before, but I can type racks, and instead of me having to look through the topology file, it says, so there's 10 blocks and replicated 3 times, and this is on rack 0, 1, that's on rack, the replica is on rack 0, 1, there's the IP address, and rack 0, 2. So this block is on, it has a copy on rack 1, and rack 2, which is what we expected, right? And this one is rack 3, rack 2, and rack 3, right? So that's what we expected, and rack 3, and rack 3, and rack 2, right? So this is now looking like what we were saying in the slides, right? So it looks okay, and I think if you inspect all of them, you'll see, you know, that's the case. I'm just having another quick look. Now, what I had done before is, you know, we had a file where it was all, when we didn't have that set, it just had default rack. And they're all on something called default rack, which I think it just means it just goes to any node, right? At any data node at random. So I had a file that was just spread out with default rack. And then I changed the configuration and restarted the file system. And it detected, it said, oh, there's a number of blocks that are not in the right place. You know, they're not being configured properly. And it started moving them around then to make them fit the policy of being on the rack where they should be, right? So this is the self-healing property that we talked about. You know, the system is constantly looking, is everything correct? You know, it's like running rules to say, you know, is it how it should be? If it's not, then we start moving stuff around and making it so that it should be how it should be. So this is without any rating. This is just 10 blocks, right? Are there any questions? And we created that with our program. It took a little while to do. We're going to do that a couple more times, and I don't know. We may or may not. Depends if we have time. I mean, again, this is something that you can experiment with, in your own time as well. And again, I don't do too much in the afternoons. Basically, I just lie down because I'm trying to get over this cold. But if you want to, if you have your computer or laptop, we can come and sit down and work through stuff. I'm quite happy to do that. Anyway, so let's just see. I don't want to give you the cold though. That's probably why you're worried, right? You don't want to catch this cold. So let me. Let's turn on the RAID, right? So what we have to do now is edit our RAID config. And I have to give it the directory, where it's going to look for. So we constructed that file. It's kind of given as a URI. So presumably this RAID node could run on any node, and because I'm giving it a URI, it would connect to the to the name node or the whatever it needs to connect to, and at this address, and then control it from there, right, remotely. But it's running on the same node, so it doesn't really matter too much. Make sure that I'm typing everything correctly, because if we put this in incorrectly, then it won't work, and we'll scratch our heads and wonder why. So I think I've got it, what we need. Okay, test DFSIO. If you think it's wrong, then shout out. Okay, so that is there. We don't have to change any of the parameters in the other file that I showed you over here. This is the the Hdfs config file, because it's already set for RS code. So the parameters would be like, so the stripe length is 10, and the parity length is 4, and the RS parity length is 4, and a little bit further down here, probably should reorder these. We can reorder them, but use MX OR code is false. So that's all good. I won't change that. But what we do need to do now is because we've sort of changed some of the configuration, we need to stop all. So this will stop the system. We'll start the DFS again. I think there might be a command where we can sort of just say reload the configuration file. That would be nicer than stopping all and starting it all again. Sometimes they do that, but I was looking around for it, I couldn't find it. So we'll start our MapReduce again. So I just stopped all and started all. Let's just kind of have a look at that file again, and I won't put where the racks are. I'll just put the blocks. So they still say replica 3. Okay, so eventually we should start sort of seeing that go down, right? Because we're expecting, as we said before, that these replicas will start disappearing. Now that we've turned RAID on, that it's going to do that. Let's have a look at the map reduce, because this thing is a... Is there anything running there? There's nothing running there. But maybe the other thing is only map reduce though. Let's go back to here. Do we see anything? Still just like that. Let's keep going. It could take a little while for it to detect and start doing something. Still only 3.
Asking for raid now.
Yeah, it should be rating now. But it might take a little while to detect. It didn't take that long when I ran it earlier. So when it takes a little bit too long, I start wondering, have we done it correctly? Oh, well, there's a rep. This one's gone down. It now only has 2. So it's actually saying the average replication is 2.8. So we shouldn't panic. Demos, it's very easy to panic in demos. Now the replication has gone down now quite a lot. So it started to do that. Now the replication of this file is all at 1. Now it should be creating other blocks as well. But the other blocks are not stored in the same place. The other blocks are stored in another part of the file system. And now here are the 4 parity blocks. So it's created them as well. They don't have any replication. The default replication was set at 1. So we've got the original 10 blocks, and now we've got 4 parity blocks. Now, let's have a look at the location of those parity blocks, because just for see what it looks like.
It's all one place.
Oh, I've already got files and blocks. Let's put locations. So it's all sort of on the one place. The placement monitor might take a little while to get around to moving stuff about, but eventually, you don't want all of those blocks on the one spot, and the placement monitor should move stuff around. While it's doing that, let's go back. So we have these original blocks of our file. We've got those blocks, and we can have a look at the locations of those. So, they're kind of spread out on different places. Looks like they're all at different nodes. They wouldn't all be at different racks, obviously, or they might. Some of them will be on the same racks. So now we sort of want to kill some and see what happens, right? So how many can I kill though? I could kill 1 or 2, or will it repair if I kill 2 of these nodes? Is it?
You could kill 1 and see.
We'll kill 1 and see how it goes. Udara is a little bit hesitant to kill more than 1, but we'll kill 1. So let's log into. I think I should exit from here. We'll log into at 146.118.97.198. If that happens to be the spot where the parity blocks were and we kill it, then we'll be killing a lot. It's not the same node as the parity blocks, so that should be okay. So let's just terminate the data node, right? So that's kind of dead. Let's go back and see what is our Hadoop file system tell us. So it still says it's okay. And why is that? It's just because there are these intervals of time, right? 30 seconds or something like that, or the block report is every 30 seconds. So until that block report comes in, or actually it's the heartbeat monitor that won't come because he killed the data node. I didn't remove the block from the system. I killed the data node, so that was every 3 seconds, and then there was another trigger on, when do we find out that something is wrong. So what has it done now? Actually, now it's still, we might have missed the point where it says that it's not okay. Because if I was kept polling it, you would see that it would say, oh, something's wrong. It's gone and replicated something down here. I'll keep going. So it's actually gone and reconstructed that. We've got 10 blocks there. We didn't. I should have kept polling, and you would have seen. Maybe I'll do on the next example, but you would have seen that. So this IP address was what? Was 198, right? So no, it still doesn't think that it's dead yet. Oh, now it thinks that it's dead. I'm not sure what it was doing before, but now it thinks that it's dead. It says that it's missing. Yeah, I'm not sure what that extra replication was before, but now it's definitely saying, no, this block is gone. So what is it going to do? It says it's corrupt. This file is no longer, now it's healthy. So in the time period between then and there, it somehow reconstructed that block on another node. Right. So these are kind of things that we're talking about before, and these are the way that it works in practice, right? If you see this in practice, there are these delays. It finds out that it's corrupted, and it finally decoded. It repaired it. What we couldn't see is exactly which blocks did it download to do the repairing, and measure some of the bandwidth. If you want to do that, you need to look more in the log files and look at the individual things that get printed out by the components, and it's a bit more detailed. How are we going for time?
We have another half an hour, more than.
So let's kind of do another code. Which one do we want to try? The MXOR code or the or the Zorbus LRC?
Even in this here itself, you want to have some idea about where it is failed, and have any questions on it? Because sometimes the way how the code is constructed, how it is used, so it depends on this particular system, right? I mean, do you see that how Hadoop is managing these data nodes? So if you get any questions, right?
So to do another code, it does take it. I have to turn the. Unfortunately, I have to turn the RAID off.
But it can actually. It took a. If you kill 4 nodes, it might take more time. Right?
Right. Well, I can't just kill. Well, you want me to kill 4? Well.
Yeah, another 3 more, and see what happens.
And we could do that. Although I just edited this file. But it might be okay. Let's try killing a few more. So let's just have a look. So it still says okay. I edited that file, and so it might not work. Let's see what happens. So we'll kill some more nodes. So can I put that up there? I will. Okay, so let's do. Probably should have a script that helps us kill nodes. we'll kind of kill it quickly. 6227.184. You want another one? 14. Let's do 146.118. 142. We'll call 3. It still hasn't detected. Well, I changed the configuration file because I was going to move on to the next code, but I don't think that will affect us because I think it only reads that when it starts up. So we haven't reset it. So it should still be doing the rating, and you know, it should still be checking stuff. So it does say corrupt. It's got at least one missing. Yeah, okay, so now it's got a few more things that are missing. So it's, you know, we're trying to make it hard for it. So, you know, misreplicated blocks, 20%. You know, okay, so let's see. Is it going to be able to recover? Now it's got 3 missing. So there are the whole 3 that I just went and killed. We'll give it a second.
So it obviously takes more time now. Because the real RS decoding will happen.
I'll just go back and we'll have a look at the locations of those RAIDs. So these are the parity blocks. The parity blocks have moved around. So the placement monitor did finally kind of push them out onto different nodes, right? I didn't kill any parity blocks, but they have moved now, right? You can see the IP addresses. Yeah, you know, that's where we're looking there. These are all different. They all were the same before, but they've moved. So, you know, the system kind of finally, it gets what we need. Let's have a look at, so, yeah. So it's still just missing. I don't know how long it might take. Oh, it's only got 2 missing now, so it's getting there. One of the things with our setup is that so it's replicated something. I didn't notice that. We saw that before. It's got a replication of a block here, and you know, I wasn't sure why it was doing that. I think I know why it's doing that now. Do you? I could guess it why it's doing that. Do you want to guess what this replication is for? Why is it replicating that block? I'm just going to guess, and you could guess too. We can investigate further and see if our guess is correct, but you know, speculate. I guess I'm thinking it's because it's transferring the block. You know, in order to do the recovery, it's got to copy blocks around from one place to another, and this might just be an indication of the fact that something like that is happening in the background. Maybe that's what. So let's just see. So you know, it does take a while. What I was going to say is that these nodes, I think I did say, they're only 1 core nodes. because I have 200 of them actually in an allocation, and I have them for distributed file system, not distributed file systems, but just distributed system testing. So they're mainly for large scale distributed systems. They're not really for high performance. So on a high performance system, this would probably go quite a bit faster. But it might have been interesting to see, you know, where these blocks were in terms of the racks as well, because you know, now that it looks like there's only one missing, but if they were on the same, you know, like, so they are spread out over the racks, and that's going to cause the transfer of the blocks to take a little longer as well. If, you know, so you need 10. How many blocks do we need? 10 blocks to, you know, to be put. So there's only so many blocks on a given rack where the failure was, and I didn't actually. I might have failed by chance all of the nodes on the same rack or something like that. You know, there could have been something like that, and we should have perhaps looked at that. But you can see that it's getting there. It's, you know, it's now it looks like it's healthy, right? So it kind of recovered from that sort of phase. So I went and I did something harsh. I killed a bunch of nodes, and finally it picks back up. So we'll just try one more code. I don't know that we'll get all the way through. So I've already turned off rating in the configuration, and I just need to sort of reset the system now, because otherwise we get into trouble with different codes being stored. So I'm going to stop all, and as well, this will, you know, when I start all, those nodes that I killed, they'll come back up. So we sort of start again from. We'll sort of just erase all of the data on the system, and we'll try this MXOR code. I'll format the name node. So that's gone. Now we'll start up Hdfs. We'll start MapReduce. And we'll go to dupe, and we'll run this process again. I would think that constructing a 640 megabyte file through MapReduce might be a little bit faster than what it does happen here, but it does take a little while. Are there any comments that you have? You're very quiet, actually, as a student. You're more make more comments on the actual maths and the coding theory than on the systems side of things. It's so I think this program can do a bit more in terms of, you know, it's constructed for measuring the performance of reading and writing from a distributed file system. It does print out quite a bit of data at the end on times taken and so on and so forth. Unfortunately, I'm not sure there's much more we can see. And maybe if I go here, or maybe I can click here, and yeah, because it's not really doing a computation, it's just sort of writing data, and so there's only one task running really, and so it's not really very efficient. It's kind of interesting, you know, I'm killing data nodes, which is killing all of the blocks on that node, and you know, if I could kill an entire rack, I suppose, by killing all of, you know, and so the kind of failure that you know, this is more like correlated failure now that you might talk about. So ordinarily you might think of those blocks, your coding blocks, as, you know, failing all independently, perhaps. You know, each one has an equal probability of failure, and so you have all the combinations of failure. You know, n choose whatever, you know, number of failures is all equal, right? They're all likely, but really that's not so much the case. And you know, some nodes we find in Nectar are more unreliable than others. You know, we've been running Nectar as well, and found that sometimes it's not that nodes fail, it's just that there's a network issue and they just can't communicate with each other anymore. So the heartbeat from the data node might not arrive. It's not because the data node's actually dead, right? It's just that there was a network problem. So, you know, that can happen as well, and it can kind of cause like a transient type failure that, you know, that is only there for, you know, may or may not get recognized. So again, those trigger points, you know, 30 seconds, how long do you know, how many heartbeats do you kind of go through before you say the node has definitely failed? Not just the first one, because that might have been a packet loss or something gone wrong in the network, just transient. So you might wait for 5, 10 or 30 seconds worth of that before you actually say, yes, this node is definitely, it's not just a short transient problem, but, you know, there's something more serious. But in any case, it can always come back up, you know, and so
this problem, so this is actually a very important thing in our design, especially the coding for such situation. So you may not want to actually recreate a node in such case. So for example, at this point, if you are if your program is using that block and you need it immediately for that purpose, then you may want to recreate just that block, right? So this problem is not been fully been comprehended. People actually, we take off a node repair. That time you're going to repair all the blocks stored in that node, and that might belong to multiple files. So you know your file can be much bigger. Whereas with the type of error that Aaron quite explained, this is also kind of a misread. So it's like, you know, somebody asked me the misread, it's the same thing. So you try to read some block, you won't get any response for it. So how long you need to wait until to decide that the whole node is down? So instead you may just want to contact some nodes and other nodes just to create the block that, you know, so you want to kind of recreate a block that you are looking for. Now this could be more efficient, and so what type of codes you to do it, in even this case LRCs will win, right? I mean, because you can only connect the local ones. So this is, you know, so you need to actually think on that direction. So that way with MXR, you can easily talk to the nodes which are in the same group, and you might even, you know, just by contacting 2 other nodes, let's say 3, right? So 2 other nodes you can recover that file. Yeah.
So as well, there is that if you remember, the data node had a parameter: how many disks will it tolerate failing before the data node, you know, fails itself. We'll just say it won't work anymore or decommission. So, you know, if the data node has a bunch of SATA disks or whatever, you know, one of them might fail, which means the data node hasn't failed. It's just some of the blocks that was, you know, a bunch of blocks on that disk are no longer available. The block report will change to indicate that. So the data node hasn't gone, but you do have missing blocks anyway. So I think you can see how this system is working. And then as Yudaya is saying, you know, how is it relating back to the kind of codes that you need to build to handle all of these sorts of things and work well with the distributed system nature of self-healing and being reliable and people starting and stopping and submitting stuff, and you know, all of that stuff that we do when we run processes and store data, so on at a higher level. I guess this is finished now. So what we can do is, and you can see it did put some times here and some throughputs. It's not very good. Throughput megabytes or megabits per second. If it's a lowercase b, I tend to read it as bits rather than bytes. Megabits per second is only 2.6. Doesn't sound very good to me, but I would want to investigate that further. It's the sort of thing that I look into. Why is that? I think it's only because there's one mapper task, and there's a bunch of other stuff that this program gives us. But let's just turn on the RAID now. Let's turn on the RAID, and we need to do a couple of things, right? So we need to do Hdfs. I need to change the parameters, yeah? So we're going to use 6.6, I think. Is that the 7.7? If MXOR code, we'll say 7.7. You can see I'm not a coding person, right? So here, we'll change to 7. Here, RS parity length. Make sure I'm doing all the right things. And then we're using MX core code. So down here somewhere, we'll say true. Yeah. In here, if you make your own coding scheme, it's here where you can change to say, oh, and use your coding scheme, you know, and put a parameter in there, and the system, you know, this config file can be read by the system, obviously, and you can, you know, there's a spot where you can sort of determine which coding scheme to use, right? So we'll say true for that. So that's for the distributed file system. I also have to, I have to put this back in. Demo is a bit clunky as a result of having to do this. I would like to streamline it a bit. I have to put this source path back in, which is and again, make sure I'm typing it right. That's what they say about open source code. Is that because it's got many people looking at open source code, presumably the bugs are less in the code. I'm not sure about that. That's a different discussion. Test.
Yeah, at least you will enter the right direction.
Data. So you're all eyes looking. So I've got HDFS master. Benchmarks, test. All right, so that looks good. So now I'll just restart the system. And I could go and check that file, so I don't want to do that. I want to do that, so and I'll do it without the racks and the locations. So again, we've kind of got a little wait time for, it's really just the same thing that's going to happen as before, but it's using a different code, so it has different properties. We should see the replication drop back eventually as it comes forward, and then we, again, we could kill certain nodes, but I'm sure what you'll see when we do that is that, it'll see them as missing and corrupted, and then it will start, repairing. If this code has a bit better ability, depending on if you kill in the same rack or not, right, and so on. So we could go and test that out as well. It'd be nicer perhaps if I had some scripts that sort of did all of this at once, so I could just run and we could see outcomes. But I think just seeing the commands and working through a bit and seeing what's going on is also somewhat useful. So it's still kind of so you think we'd all be using Hdfs to store our data? It seems more reliable, and is it? It seems more complicated as well, obviously. So some of the replication has started to fall back. I think it will start happening quite quickly now. And then we can check the parity blocks. Do we expect to see 7 blocks for the parity? Is that what? Yes. That's correct, right? So there are the blocks. Let's have a look at the locations. So they're still all in the same place, and I can put racks there. So they're all on rack 3, but eventually they'll, as we saw last time, they'll get pushed around to different places. I guess the code, I mean, you can comment, the code requires that the parity blocks be on different racks. Is that? It could be anywhere. Is that what, so they might just go, obviously they're going to be pushed around so that, they're not sitting on the same data nodes as other things, to spread them out as much as possible, so a single data node failure, fails the least number of blocks of this file, right? So that's kind of what it's going to be. So we could kill if we want. How many can we kill in this case?
No, 2.
Any 2?
So yeah, we had a discussion now. Can 3 be killed? But then we need to kill in a proper way.
We need to kill in a proper way, do we? I can't just pick randomly.
We can write over there and say
all right,
which other failure patterns that the code can.
Oh, but I like to just kill randomly.
So let's say this is 1, 2, 3. So we have these are the parity. So this is P1, 2, P3, P4, P5, P6, and P7. So 3, if you kill 3, that can recover. I mean, in fact, you can even kill 1 to 5. It will recover.
I'll tell you the problem. I don't know immediately which blocks correspond to which parities by looking at this.
So what we do, we can randomly choose something. If, for example, if you choose, say these 2, maybe including these 4.
Is it that you think that the first 5 blocks is the first row?
I think so.
You think so? So you think I could kill the first 5 blocks and this thing will recover? Is it?
Yeah, well, let's see. If it is not, for example, if it is not in the same row, then it can't recover. So for example, then there will be 2 over there. Then we will say, for example, what happens? Can this be recovered? Yes? Up to 4 can be done, right? Like this? This can't be done. Or can be done. Because this one we can do. So that's pretty interesting.
Any 6 cannot be recovered.
Any 6 cannot be. Up to 5, any 5 can be recovered?
Any 5 will be recovered.
I really see that's, let's see how that is true.
The first and second column, I form it, then it is not, I am not able to recover.
Okay, first and second column.
Whole column with parity.
Am I going to start killing now? Have we decided which ones? I don't like this. This is Unix is quite bad. Kill, it's a bad word, right? I mean, we don't like this word normally, but that's the word,
So what you are saying is that if these 2 are killed, then that can't be recovered. But however, otherwise any 6 you should be able to do, right?
Any 5, right?
Any 5, Any 5. I mean, what I'm saying is, if what about this one? Yeah, so even 4, some 4 you can't do.
Yeah.
That's what I was going to. So really, with MXR code, you see what is at least what is the lower bound. So this is another thing that you can think about. What is the lower bound? It can always detect 2. 2 is lower bound, and the horizontal side it's only also 1. It's actually 1.
So 3 is also possible.
3?
3 is also possible in
Most cases, but
if you kill 3 in one row, or if you kill like this L shape, then also this recovers.
Okay. But anyway, we'll don't need to write the numbers again, but so this this 3 can't go, right?
Yeah, 3 will.
They can recover.
You can recover. This can be run, but this way also you can.
Yeah.
So any 3 should be possible.
Yeah.
Any 3?
Any 3 should be possible.
All right. Let's do any 3. Some of the parity blocks have started moving around now too. I think you could see, you know, it started, so I'll do the first 3. Any 3 for me always just means start at the top and go down the list, right?
Yeah, any 3 should be.
All right, so
It might take more time. Any 3.
well, we have a little bit of time left, so.
So it will be a good task to kind of write down all possible patterns that it can correct. Any 4?
Any 4 now?
No, I don't think any 4. Let's see. Oh yeah, any 4 also. Yeah, you're right. Any 4 will be possible.
Can you get it? You have to get the story straight.
1, 2, 6, 7. 1, 2, 6, 7. Yeah. So that we had talked about it. Yeah. That's not possible. Okay. So, but all 3 can be done. Parity blocks. Yeah. So did you kill 3 or?
Well, I'm getting there. I should have a script that helps me kill.
So we call it like 7, 7, and so on. So if I do 7 parity and 5 plus 2.
Yeah, but this is 7 parities.
Yeah.
But if it is a normal MDS code, how much error it should target?
10.
No, there are 7 parities. Right?
7 parities.
So how many errors it should target? 7. But now you only get 3. So obviously there will be degradation in terms of MDS performance. But what you gain is the performance, like you can easily recover in case of a single error.
So what I'm asking is if it's 5 plus 2, 5% columns with 7 parities. So that's why I'm calling it 7, 7. So
7, 7 MXR. So let me write down. So you said 5, say 5 first?
2 parities, yeah.
2 per bit. Or just if you took only these 2.
No, so there are 7 parities.
Correct.
What if I increase the number of columns? Let's say I increase 1 more column.
You increase 1 more column.
1 more row, let's say. So 15 information.
So you add 1 more row here. So 15, and there's 1 more parity. Huh.
So there will be 8 parities.
So now, no, there are only 3 parities plus now we add 5 more, 5 parities.
What will be the dimension?
Now this one, so obviously there will be now P, so how many? 3, 5 plus 8 parities, and this will be 15 plus 8. Length will be 23 and 15 code. So k is 15, n will be 23. Yeah, yeah. I mean, it's basically you are adding parities like this, but this is not MDS. So obviously, by just adding an additional thing won't help. But in other type of code where what people have done it is basically increase this and have only one. In that case, you will only be targeting single error faster and sometimes double error. So if your errors are only less, 1 or 2, sometimes you use this to improve the performance mainly. But remember, as you increase it, the number of nodes you need to contact a repair one also increases. So that way, just by arbitrarily increasing rows may not always help.
It recovered,
yeah.
right?
It recovered?
From those three.
Three recovered,
those
yeah.
three that I could see that it could do that too. By using the
yeah.
by the parities in the row there, right?
Yeah.
Okay. It was quite quick too, I think, the recovery.
So recovery, yeah, quicker than the RS record, yeah. That's why. That's because of the the operations are simply XOR, nothing more. So, whereas on the other hand, SOAR was the code has more.
More downloading to it, yeah.
Because SOAR bus has to download 5 nodes to do.
But those parities that it downloaded in this case, I think they were being downloaded from the same node as well, so that if they were spread out on different nodes, it might have been even quicker because you'd have got more parallelism in the downloading. You would have been able to download multiple, at the same time. So it did seem to recover quicker than the previous example.
This is a good point I want to ensure. For example, so what you mentioned is, say you have a parity. If it is in the same node, and also the data is also same node, now you need to get all this data in a sequentially. Whereas if it were completely spread around, you could use a parallelism of read. So while I'm reading one, I can also read parallelly together. So that will improve. So in fact, we had seen such behavior in our results, and with MXR, actually having all these data blocks and parity blocks in distinct nodes will actually help. But sometimes if they're clubbed together, you might think that now data is available locally, but still it will take the same amount. It takes actually more time because of the sequencing. So that's you need to give attention to, while designing the code in the recovery, how the the sequence of all this kind of scheduling the data download also matters. And so in fact when I discuss the results tomorrow, I'll show you how the read and write and also this performance affects the complete node recovery. Yeah.
I think you see as well that you might think that, well, for a high performance file system, this is somehow taking a long time, right? But you have to imagine there could be many thousands of files on this system, and all of these actions are all happening in parallel. And so for a lot more files, the time that it takes to do all of these things wouldn't be all that much more. So for one, there's a certain overhead when you go to use these systems and you sort of see a jump up in time for just one file. It takes longer than if it were to run on a single system or something. But this distributed system is obviously going to be able to cope with many, many files and a large amount of data. And so adding more and more, you won't really see, you'll take the same time even for a much bigger sort of file or a much larger number of files, right? So it'll be like that, a little bit like our map reduce. I did a word count of a file that was twice as big, and it didn't take twice as long or something like that. We were using more parallelism and so on and so forth. So if I killed the data node that contains all these parity blocks, it will just reconstruct them all, I guess, right? That's okay. Yeah. That one, is a clear case where it could still work, right? Because it's got all the data. It just needs to reconstruct the parities.